Yeah, thanks for the invitation. I'm very happy to be able to come and talk to you all today. Yeah, so as was just said, I'm going to talk to you guys about normal simplices and moduli of hypersurfaces. And essentially, the aim of today, we just want to take a very specific path, like one of the many connections between these two areas, being one of which being combinatorics, and the other being geometry. To be a little bit more honest, I suppose, we're actually going to be going between discrete geometry and kind of algebraic geometry. And yeah, there are many different ways in which these areas are connected and really intricately connected. We're just going to take one quite very explicit, quite nice and simple connection between the two, and hopefully, yeah, be able to gain a bit of understanding of geometry using these combinatorics and these kind of more rigid structures coming from the discrete side of things. So yeah, when I say discrete side, I mean combinatorics, and geometry is the algebraic geometry on the other side. So yeah, so the talk will be split up into essentially two different parts. The first bit concerning combinatorics and lattice polytopes. In particular, we're going to look at lattice points of polytopes and lattice points of dilations of polytopes. Okay, and then yeah, we're going to look at related questions in the geometry side of things, and we're going to try and understand so-called moduli spaces of hypersurfaces. Now that's a lot of kind of words which we'll go through slowly, and we'll introduce each with lots of kind of examples, and yeah, to give a nice kind of introduction, and we can see how these two things will benefit each other. So the first one, lattice polytope. So this is will be familiar at least to look at for most of you. So a lattice polytope is taken by, so for today we'll take, let's say, R points inside Z to the N, okay, inside the standard lattice inside Rn, and we just consider the convex hull of these points, right? So it doesn't have to be, but if suppose we've taken the vertices of, so these PR, there we go, so now I can draw. So these P1 to PR here to be the vertices here. We've got these 4 points here, and we consider the convex hull, which is all the points kind of inside, so it's the biggest convex body with all of these points. Smallest convex body, sorry, with all of these points. Okay, that's yeah, that's a lattice polytope exactly. And then on the other side, the main objects of study are going to be things called hypersurfaces, which are kind of very simple examples of what are called algebraic varieties. And yeah, so essentially what we mean when we say a hypersurface, we just mean the vanishing locus of a single polynomial. Okay, so here's a pretty standard example. We take a polynomial which is y squared minus x cubed minus x squared. Okay, this is a real polynomial in two variables, in x and y. And the vanishing locus of this guy is exactly all the points x and y in the plane such that f, the polynomial, vanishes on these points. Okay, and we've drawn we've got a picture just to the left here. So this locus here is exactly all the points in R2. So this is R2, where this polynomial vanishes. Okay, so here you see, right? So we can write down the equations, and we have the geometric picture on the other side. Exactly. So this is a rather basic example. It's what's called a plane curve. It's a nodal cubic. So it's singular in particular. So we have some kind of interesting non-smooth geometry going on here. So we'll talk a bit about these kind of things as well later on. And a slightly more involved, kind of more beautiful standard example here is, I hope this is the Klebsch cubic. So this surface here has a name, and it's the vanishing locus of this polynomial here in three variables. Okay, it's in three variables, so it forms a locus inside R3. And this is an example of a cubic surface, which are very well studied. And when we like here, we consider the real locus. So here we're considering only points inside R3. So the real numbers here, we get rather nice pictures. Here we can start to see that actually the geometry of these things is like quite complicated and quite beautiful. And yeah, so these things are somehow, they have naturally worth studying. And so both of these examples here, we've got, we're working over the real numbers, just so for the advantage, so we can draw the pictures. But in general, we'll actually be considering polynomials over the complex numbers. So in general, we work over C. Okay, so what this means is that so the coefficients of the polynomials are going to appear in these rings. So, and we can take an element inside here. So this is going to be a polynomial with complex coefficients. So this is just equal to some where we have let's give some indexing here. So we take these positive numbers and we have, it's just some finite collection of monomials with complex coefficients, right? So these are complex numbers and we have, so these are the objects that we're going to be interested in. Okay, that's a 0, should be a 1. Okay, so that's the introductions. We've seen the kind of things that we're going to be studying, and yeah, exactly. So my angle as an algebraic geometer, I'm not an expert in discrete geometry, but I'm interested in kind of taking these polytopes and trying to learn things about these algebraic hypersurfaces, yeah, and geometry on that side of things. But first, we're going to start talking about polytopes, and in particular, I think a class of polytopes called normal polytopes, which we'll come to define. So we start with the definition of a polytope. Okay, as we said before, it's a convex hull of R points in the lattice. So each of these points are here. Okay, and if you want to write it out explicitly, you take linear combinations of linear combinations of these points, such that the coefficients are non-zero and they equal and they sum to 1. Okay, and this will give us some locus in Rn. And like this, you can describe all the polytopes. So one operation we can carry out, okay, on a polytope such as this here is dilation. Okay, so dilating is, as the name would suggest, you take the polytope and you essentially expand the polytope by a fixed number. So concretely, that looks as follows. So you take a non-negative integer, a non-zero positive integer, sorry, and the kth dilation of P, our polytope here, is going to be, so in particular, you take the R points, you scale them, you multiply them by K, and you take the convex hull, okay? And we've got a picture here, okay? And this is what it looks like. So for a two-dimensional polytope, so a polytope in a plane, here we can dilate it by, you can take the third dilation here and it would look like this, right? So it's essentially the same shape, just bigger. We've scaled it up. And then one interesting thing to study, and one huge area of study in discrete geometry, is the lattice points of these dilations, for example. And this is a whole area. It's called Earhart theory. And let's run through that quickly. So we write down a function here, okay, E, P, and K. So the function eats a polytope and a positive number, so non-zero positive number, and K, exactly. So what do? We take the kth dilation, so we scale it up, and then we intersect it with the lattice which it sat inside, okay? And this number E, P of K is the number of lattice points in this larger polynomial, okay, in this larger polytope, sorry, okay? And as it turns out, this function here is actually a polynomial in K. So when you fix the polytope and you want to know you would like to know the number of lattice points in a kth dilation, then this is actually a function which you can write down. It's the degree, it's a polynomial of degree D, where D is the dimension of the polytope. And this is this polynomial, which one can write down, is called the Earhart polynomial. Okay, this is quite it's a large area. People study these kind of questions specifically, and we're going to be looking at a very special part. So we're going to be interested in, essentially, we're going to be doing some of this we're going to be playing around with polytopes in these ways. We're going to take a polytope, we're going to be scaling it, and we're going to be looking and interested in the lattice points. Okay, and this is what now we're coming on to normality of a polytope. Okay, so a nice geometric way that we can gather together all these dilations, okay, is in the cone. And what we do is you take the polytope P, okay, which is the convex of P1 to PR, you put it in a dimension. So suppose it's full dimensional. This may not be necessary, actually. So just take P, suppose it's in Rn, and we're going to put P in Rn plus 1, okay, and you're going to take it, you're just going to put it at put P at level 1, okay, so you're going to add a dimension and you're going to put it at so you're going to set that new dimension, that new coordinate to 1, and then you're going to take the cone over these points, okay, over this polytope here. And so, I mean, maybe it's, to write it down mathematically, it's not difficult, but not very enlightening, maybe. But you can see it almost directly from a picture, right? So we've taken P, this two-dimensional thing, we put it in 3 dimensions, and we've taken the cone over it like this, okay? And exactly, so here, and then you can imagine that up here, we're going to have the third one that's going to be even bigger. Like this, okay? And this way we can, in a geometric way, we can gather all the scalar, all the dilations of P, like this, okay? Okay, so now, as I said before, normality is going to be about how the lattice points of these dilations behave, okay? So we say a polytope is normal, okay? So if for every dilation of it, so for every K, then we consider KP, and we consider the lattice points of KP, okay? So that's this here. So we consider the lattice points of KP. Then for every lattice point, okay, there have to be K points in the original polytope, K lattice points in the original polytope, such that P is equal to a sum of these K points, okay? This is the definition of a normal polytope. And now we can try and imagine what's going on here. So what that means, so if we set K equal to 2, for this to be for P to be normal, what it means that every lattice, suppose we have a lattice point here, okay, inside 2P, then we need to know, so if P is normal, then we know that we can choose 2 lattice points down here. Let's suppose it's this one and this one. And when we add them together, so let's call this P1, P2, and this P, okay, little p. And then P is got to be equal to P1 plus P2, okay? And then you generalize this for the higher things, okay? So this is why, again, like these pictures, collecting them all together geometrically is quite nice in this cone. Exactly. So this is what normality would mean for this second dilation here. Okay. So this means that every lattice point of a K dilation can be written as the sum of lattice points of your original polytope. Okay. And here's another kind of stupid example. So we start with the polytope, which is given by the interval. So it's contained inside R1, and it's given by this polytope here. Okay, 0, 1. And we can see very easily what the scalar dilation is here. Right. So 0 to K is going to be the scalar dimension. Okay, and here it's quite clear, I think, that any integer, so integer point of this new polytope can be written as exactly K. K. Guys, of this one and this one, we've got a 0 and a 1. Okay, it's not difficult. Okay, so now here we're gonna restrict to a certain class of polytopes. Okay, the most basic class of polytopes called simplices. Okay, and a simplex is just it's a higher dimensional triangle essentially. So it's a it's an n-dimensional polytope with n+1 vertices. Okay, so you think about a triangle sits in the plane, so it's 2-dimensional and it's got 3 vertices. The tetrahedron, which you see here, okay, is 3-dimensional and it's got 4 vertices, and all of their faces, so their facets, their highest dimensional faces, are simplices of the next the dimension 1 lower. And these are essentially, these are basically the most one of the nicest classes of polytopes. But as we'll see, there are still some questions which we want to understand, and these questions actually, which, as we'll see, like I stumbled upon by trying to do some algebraic geometry. Okay, so here we have this simplex with its n vertices, and here we have an example of a standard simplex. Okay, so you take so you imagine yourself in 3 space. You take the origin, okay, so you take the origin, which is this point here. You take the unit vector on each of the axes, and then you take the convex hull, and you get the a standard simplex, a rectangular simplex. We'll define these in the what's coming up. Okay, so now here's a related definition to normality of a polytope. Okay, and this is so we say that a polytope is very ample. Okay, if there exists a k0, so a positive integer, such that for every integer greater than k0, okay, we have this property that when we take a lattice point of the kth dilation, then it's a sum of exactly these points. Okay, so I mean, this is essentially like eventually normal, right? So it's so this would be to say that if a polytope was very ample and the k0 was equal to 1, 1 or 2, then it would be normal. Okay, so this is like eventually the polytope is normal. Okay, and so in this way we can see that P being normal implies P being very ample. Okay, and so the one area which we'll come on to talk about is a class of very ample but non-normal polytopes. Okay, so this it's not an equivalent. It's really a strict. It's only in one direction. And then the second remark to this definition is that if P is full dimensional, okay, and then so say it's n-dimensional, so it's set inside Rn, then the n-1th dilation of P, okay, is normal, and therefore the nth-1 dilation of P is very ample. Okay, so what this says is that okay, well you start with a polytope, and maybe it's not normal, maybe it's not very ample, but you can scale it by at least n-1. Well, I don't know, how do I phrase that best? So you have to scale it by at most n-1 in order for it to be normal or very ample. Okay, and so exactly. And so the first example of in this class of very ample but non-normal polytopes was given by Bruns and Gubladesi. Sorry, it's a Georgian name which I can't pronounce very well. And this was in 2002, and it was fairly recent, and it was like 5-dimensional. And since the same 2 authors found a 3-dimensional example, and in the last, there have been kind of like results kind of coming in for the last. The last one was about 6 years ago. And the early 2010s, there were still some examples, like new examples, kind of studying and understanding this relationship between the two coming out. So. And there is an ongoing goal, okay, which is a bit somehow where the talk today is aimed at. So with the search for a non-normal but very ample simplex. Okay, this we don't know if this exists. So in general, there are algorithms actually. There's this very nice paper by Bruns called "The Quest for Counterexamples in Toric Geometry" from 2013, and in this there's a very nice algorithm described to come up with very ample but non-normal polytopes. However, this algorithm won't produce a simplex for you, at least not. It never does. It hasn't so far, and so there is still an ongoing search for a non-normal but very ample simplex. We don't know if this exists yet. So there are some partial results in this direction. So Agata showed that this cannot exist in dimension 3. Okay, so when you restricting to a certain class of simplices, so Agata's results actually written in the algebraic geometry language. So one can't. So you have to restrict to a certain class of simplices, but a big class of simplices, and this cannot exist in dimension 3. So that is to say that normality is equivalent to very ample for these three-dimensional simplices. And okay, exactly. So, and then one other result in this way, so moving away from simplices and back to general polytopes, is that, so if we take a polytope P, okay, here P, and we suppose that P is non-normal, but it is very ample, then we can define what are called holes of P. And what this is somehow the discrepancy between, so these are exactly in between, so K0, so we suppose that K0 is as in the definition of very ampleness, that is to say for every K bigger than or equal to K0, P inside these K dilations is equal to a sum of lattice points. Okay. Is equal to a sum of lattice points, okay? But then what that means is, and we take this to be minimal, okay? So this is really minimal with this property. But this means that we have a finite set, okay, of polytopes between P, 2P all the way up to K0 minus 1P, okay? And in these polytopes, okay, we have lattice points which cannot be written as such a sum, okay? And this collection of lattice points are called the holes. Okay, so this is how we define the holes of a non-normal, very ample polytope. And it was shown in, I think, 2013, the paper came out, that so long as the dimension is greater than 3, okay, and we take the number of holes to be just greater, so any number of holes, then there always exists a non-normal but very ample polytope with exactly this many holes. Okay, so there's a construction where you can cook up these examples. Right. So then, yeah, if there are no questions, then I'll move on.
So Dominic, maybe I have a question. So what I mean, in terms of algebraic geometry, maybe you're going to say that, but how should I think of these holes? I mean, what on earth are these holes again?
So these holes are going to be exactly, so this in algebraic geometry, this corresponds to projective normality failing, right? Of the corresponding embedding of the toric varieties. So this polytope is not just giving us a toric variety, it's giving us a toric variety embedded in something.
Yep.
And but this normality condition corresponds to the projective normality of that embedding. And so I'm afraid I can't give a better answer than saying so which means that the associated homogeneous coordinate ring is not integrally closed, right? So this is not, and so these holes correspond to exactly where that's going to fail.
Right.
For a geometric
So
interpretation,
this is not, there's not like some kind of base locus or something or other, or there's no.
Yeah, possibly.
Okay. Yeah, don't worry.
I'll have a think about that. Yeah. Thanks for the question. I saw one more in the chat.
So okay, so maybe but you did say that Okada was thinking of this in some kind of different language. So, but he didn't have holes, right? That wasn't the result of that holes, or
it was the opposite. It was the non-existence of holes. So it was when very ample implies normality. So it's when essentially and that was really only a way to projective spaces. So that was that exactly. So there is some kind of numerical condition where you can just be sure that if you have a very ample bundle, then it is then the embedding is normal essentially. That's the yeah. So it's kind of the opposite of this thing. It's ensuring that these holes don't appear. Exactly. And praise, to answer your question on the normality. So yes, exactly. So this you can always it depends what K. I don't know exactly what. So if K normality is the normality of the kth dilation, then yes.
Yeah.
Okay, great. Then we'll move on to a few. So now, yeah, I'll talk about. So I've been thinking about these things. I came across some questions about these simplices and the embeddings which they correspond to during my PhD thesis a few years ago. And this very ampleness was a very important property for me. So the geometry, on the geometric side of things, this was really, this was crucial. And so I started kind of playing around and experimenting with some software called Polymake, which is Polymake is a mathematical software. It's free, open source, and yeah, it's working with discrete geometry, polytopes, fans, graphs, all sorts of discrete polyhedral geometry, and doing some kind of large scale. Well, first of all, just trying to because figuring out the normality of a polytope is really not easy. Like to do it by hand, it's really it comes down to lots of like additive number theory, especially with simplices. You end up just trying to you can go a bit crazy trying to figure out these things out by hand. So computer algebra and computer mathematical software really helped here. And in the end, I kind of, out of curiosity ran some larger scale experiments, like just kind of testing loads and loads and loads and loads of these simplices, and trying to find some of this, trying to find some counterexamples to these statements. So we'll talk. So I'll talk you through a bit of what those things were. So we take three non-negative, so three positive integers again, and we're going to define a simplex. Okay, this is called a special kind of simplex, a rectangular 3 simplex, right? And we take the origin. So as a vertices, we're going to take the origin. We're going to take the 8th unit vector, the bth second unit vector, and the c third unit vector. Okay, so it looks like this essentially. So this distance here is a, this distance here is b, and this distance here is c. Okay, and we just take so it's called rectangular because of this corner here. Okay, so this vertex, because we've got the corner of a rectangle going on here. Okay. Okay, and so the first example, so it was claimed erroneously in some by a few people that actually, so we had this result, right, for projective spaces and for smooth toric varieties. Those of you, I'll just make a smaller side comment, which says that line bundles on such varieties, they are very ample, if and only if they're ample. Okay. And this was claimed to be true for also kind of mildly singular toric varieties, so weighted projective spaces in particular. And this is actually, this is not true, okay? What that, in terms of the language which we were using on the last slide, what that is to say is it was claimed for a certain class of simplices that they were always very ample, okay? And this turned out to not be the case. And there was a counterexample, I think the first counterexample was given by Ogata, in a series of papers stretching between, I think, 2007 13. And one of this counterexample is exactly, so it's very simple, like a very basic one somehow. But the reason why people didn't come up with it before, because on the algebraic geometry side, it's not such a simple example. But again, hopefully we'll have time to see that later. So, and it's the convex hull, so we take 0 and we go 2 along in one direction, 3 in the other, and 5 in the other. And this is an example of a not very ample, okay, in 3 dimensions. From the result we discussed before, it also means non-normal, okay. And from the other result that we discussed, so it's 3-dimensional, and so if we take the second dilation, then we know it's going to be very ample, okay, and normal. So so this is quite a special example, and this was so. You can either check, really can check this by hand, okay? One has to take an alternative definition of very ampleness, which I haven't given, one which lends itself to checking by hand, but one can check this by hand, but I would recommend using a computer, because it's honestly quicker to learn how to use Polymake and type it in. So exactly, so here I'll just give a very quick rundown. So here's the polytope, okay? So new polytope, and I fed it the vertices. So here's 0, here's 2, here's 3, and here's 5. And then I can ask it essentially whether so Polymake can tell you whether a polytope is very ample. It can also tell you whether a polytope is normal, okay? And then we get it to print it here. So very ample, false, and normal, false. And this is very much more convenient than doing it by hand. Exactly. And now so we'll have an associated definition to this kind of failing to be very ample, okay? So we're gonna introduce a number I, okay? And it's gonna be the minimum number such that K is very ample, okay? As we've seen before, this is definitely less than or equal to n-1, okay, where n is the dimension, because once we scale it by n-1, it's normal. And we're going to call this the very ample index, okay? And this is essentially how many times you have to dilate before you end up with something very ample. So again, on the algebraic geometry side, this is what power of the line bundle do you have to tensor it by to get very ampleness, okay? And for those of you who kind of like these questions, this is where there's a very strong connection to Fujita's conjecture in this context, and indeed that would be a whole other talk. There's some partial results for singular toric varieties on the Fujita's conjecture, but it's still there's still unresolved work still to do here. So this very ample index would be the number. The Fujita number. Okay, so now we're gonna put some requirements. So A, B, and C we're gonna take to be co-prime. Okay, and a first guess after doing some experiments is that for P, so to be not very ample. Okay, so we assume that P is not very ample. Then P has to be of this form. Okay, for so actually this wasn't strong enough. Sorry, that should have been replaced. So we're going to take each of these to be prime, so distinct prime numbers. So then if it is not very ample, then it has to be of this form here, okay? So it has to be of P of like this here. So now this is a very, very small, very, very long list of kind of examples and test cases that were done to try and figure out what was going on with these simplices. And here you see the numbers A, B, and C, and here you see the very ample index.
So these are some kind of weighted projective spaces, or
exactly. And here you see the weighted projective space vector.
Oh, okay, cool.
And this multiplicity. So I mean, in this case, because we're dealing with threefolds, you know, the index can only be 2, right? So there's not going to be much interesting. I haven't included at all anywhere. There's a whole bunch of results with exactly analogous construction for fourfolds, for weighted projective fourfolds as well, where you get some with multiplicity 2, so some with multiplicity 3. You really get everything, but it's completely set. So you really have to construct these polytopes or these weighted projective space vectors in this specific way. So you take numbers and you multiply them together in order to be able to get a Cartier divisor, which is not very ample. You have to construct it this very specific way. If you just run big tests in testing even all weighted projective spaces, you almost never find. I mean, it's almost always the case that the generator of the Picard group is very ample. But this is not always there. This is not always the case, and it was me and a colleague, Lars Kastner. We were looking at this example of Agata, and we kind of, it was given as the weighted projective space 1, 6, 10, 15, and you see that those 3 decompose in that way, and we said, okay, well, let's just try and do that, because I think.
The Cartier divisor I think on this is the one I'm thinking of is O of 30 or
yeah, is O of 30, but only O of 60 is very ample. Yeah, exactly. Yeah, and precisely, exactly. Yeah. Okay, yeah, and another key point is it would have been lovely if all of these polytopes would have been non-very ample. Okay, but they're not. Unfortunately, there are examples where even when you take prime numbers here and non-prime numbers, so I really got this wrong. I think I wanted co-prime here. I've made a mistake, so forget that. So yeah, co-prime. There are examples of vectors here, even with all of them prime, where you end up with a very ample polytope. So it's not going to be that simple. Exactly, and since we're threefolds, from Agata we know that very ample is equivalent to normal. And there's a paper on exactly these kind of simplices, which gives some conditions for such simplices to be normal. So there are partial results out there and things to understand. And one can show quite explicitly exactly that PABA. So if we construct this polytope here, this is very ample. So we have some. So we can say something about this. We can look at some of the things, but not very much. Not very much. And I mean, we have. Yeah, I mean, I've been warned several times about studying questions like this, since, especially for simplices, because essentially it comes down to number theory is what, and looking for these this kind of simple additive number theory, and it can get very, very complicated. So there are reasons to be wary with these kind of questions, but with amounts of data like this, I think it's quite promising that we've been able to prove some partial results, and yeah, and there's hope for the future. Okay, so now let's move on to a bit of toric geometry. So we're going to discuss toric geometry without ever saying toric geometry. Okay, and this is one path from discrete geometry in these polytopes to algebraic geometry. Okay, so we start with a lattice, z to the n, and we're just going to consider these these integer vectors, so of I just can't get this right. This time it's non-negative because it's greater than or equal to 0. Sorry, I always it's messed up. So non-negative in a vector of non-negative integers. Okay, and we can put this inside this ring of polynomials here. Okay, and we do this just by taking a vector, so a vector which looks like a0 to an, and we send it to its associated monomial. Okay, so thinking about this set of vectors is exactly the same as thinking about these monomials. Okay. And what this means is, so for a polynomial here, and so a polynomial we can write down in general like this. So it's just a finite sum. So here we need to say like finite, sorry, sometimes this happens. This is a finite sum. So which means only finitely many of these alphas are allowed to be non-zero. Okay. And associated to this polynomial, we get a bunch of these monomials here. And so what this means is we have this kind of discrete world here, and we can step over to these to the polynomials, which, as we saw, give us very like non-linear, kind of complicated geometries. Okay, and to this polynomial, right, we have this associated hypersurface, which we defined earlier on the first slide, and this is just all the points in Cn plus 1. I do beg your pardon. Okay, such that this polynomial vanishes on this point. Okay, and this is a hypersurface inside Cn plus 1 again. Okay, so again, here's an example again, and this time we'll see. So this Klebsch cubic that we saw earlier, it's the sum of 4 monomials, and we can just write down very quickly the associated vectors here. So we've got 2, 1, 0, 0 because we've got z to the power of 0 and w to the power of 0. Here we've got 0, 2, 1, 0. Here we've got 0, 0, 2, 1, and here we've got 1, 0, 0, 2. Okay. So you see that this kind of thing to look at looks very complicated, but essentially, in essence, we can boil it down. We can communicate what it is just in these 4 vectors. Okay. Granted, these don't have any coefficients, but we'll forget that for a second. Okay. And in this way, we define the Newton polytope associated to this hypersurface. Okay. So a Newton polytope, we do exactly the following. So we look at f here, and we look at all of the monomials with non-zero coefficients. Okay, we take their corresponding vector, and we take the convex hull. Okay, so in fact, this is going to be contained inside the positive, so the positive orthant, because we only allow not Laurent monomials, but only normal monomials. Exactly, and this is exactly one way that we go from we we can reduce f to some kind of discrete geometric object. Okay, so in this case, for example, the Newton polytope would be the polytope associated with the convex hull of these four points here. And even though so it's a three-dimensional polytope, because I mean, in the end, this is also a simplex. It's hard, not necessarily immediate to see that, but it's got four vertices. So these four things are the four vertices. And in general, this would be this sat inside R4. So, okay. I think. Okay. So, and now let's go the other way around. Okay. So we've seen how when we're given a polynomial f, we can associate a polytope, okay, just via this construction here. And we can go the other way, right? And we're going to fix a polytope in Rn plus 1 greater than or equal to 0. And so we fix here a lattice polytope again, okay? And we can define a vector space, okay, as follows. So we just take all polynomials, okay, inside this whole polynomial ring, whose Newton polytope is a sub-polytope of our fixed P, okay? And this way so this is a finite dimensional vector space, because as a basis, you can take all the lattice points of P, take their corresponding monomials, and any polynomial in this vector space is going to be some of these ones here. So it's finite dimensional vector space, and it parameterizes a certain class of polynomials, and therefore of hypersurfaces. Okay, and in fact, this is a very good way to class it. We say these are hypersurfaces with Newton polytope P. Okay, so for example, now let's take this. We take this one here. So this is going to correspond to x0 to the 3. Here we've got x1 to the 3, and here we've got x2 to the 3. So what does this look like? This looks like, I'm not so good at drawing straight lines, but here we put x0 to the 3, x1 to the 3, and x2 to the 3. In between, so if one does the computation, one finds all of so the lattice points look like this. Okay, so this lattice point, for example, is x0 squared times x2. This one is x1 squared x2. This one in the middle is x0, x1, x2. Okay, and so VP in this example is equal to the homogeneous polynomials of degree 3. Okay. So I said I wouldn't talk about any toric geometry, but essentially what's going on here is that the toric variety associated to, so I'll just say a quick aside, okay? I don't want to go into toric varieties and everything, but the toric variety associated to this polytope is the plane, P2, with a polarization given by O3, okay? And these polynomials are exactly the sections of that polarization, okay? So this is what's going on somehow behind it. Okay, how am I doing on time? Okay, So, lastly, we're going to talk about discriminants, okay, and how discriminants tie into these things. So, a discriminant is something which is essentially so we're going to look at VP. Our vector space is VP, right? And these are big vector spaces of polynomials. And we're going to go over, a discriminant is going to look at VP, and it's going to discriminate against different types of polynomials, so singular and smooth as it's going to be. So this is where the name comes from. And now we wouldn't have to, but in order to avoid technical problems, we're going to exclusively work with simplices and a special type of simplex. Okay, so we're going to fix a vector called A. Okay, so again, it's a collection of n+1 non-positive integers, and we're going to say D is equal to some multiple of the lowest common multiple of all of these weights. Okay, and further we need to define DI. Okay, we're going to define DI to be D divided by AI. Okay, so exactly, and that's this what's. So in the polytope, so the polytope here is this is a simplex. It's an n-dimensional simplex. And here it's actually sat inside n+1, sat inside our n+1 space. So it's non-full dimensional. So it's like, if you imagine here, we have 3 space. It's like taking this point, and this point, and we take the convex hull. Yeah, so this is a two-dimensional simplex inside 3 space. To give another example here, so here, can insert some space here. Okay, and then we can say, so here to give it the monomial kind of understanding. So here, this is going to be, so the weight, so this polytope here is going to be the convex hull of 4, 0, 0. So that's D0. So this is X0. This is A0, A1, A2. So D0 is equal to 4 divided by 1, so 4. Same deal with A1, D1. Okay. But then the last one is divided by 2. Like this here. Okay. And so what this looks like is a kind of a fairly, it's a simplex, but it's a bit fat and squished. So here we've got, again, instead of using, so I'll refer to the lattice points as monomials. So here we've got x1 to the 4. Here we've got x0 to the 4, x0 cubed, x1, etc., etc., x0, x1 cubed, and here is x1 to the 4. Here we've got x2 squared, and we've got 1 row in between. And this, for example, is x0 squared, x4. It would be x1 squared, x2. Sorry, that should be a 2. So this is what. So this is the simplex as it looks like. So it's a two-dimensional simplex. You can understand it very well. Exactly, just to give you an idea of what's going on. So now a quick definition. So we say a polynomial is singular, okay, if there exists a non-zero vector in Cn+1 such that when we, so the differentials don't all vanish at the same time for this point, okay. So it's a very standard, so you can imagine a polynomial, you can see it as a function from Cn+1 to C, right? Just by evaluating the polynomial. And essentially you're checking whether this function is singular, not as everywhere except from the origin, okay? So we have this notion, you just have a bunch of polynomials, a bunch of functions, you can compute the differential, the derivative. If all the derivatives vanish, then it's singular, okay? And we're interested in, and then here's an example where this does happen, okay? So here, A0 to A3, and D is equal to 3. This is the Cayley cubic. And it's got 4 singularities, okay? The singularity, so the points where all the differentials vanish, you can imagine just quickly what's going to happen if you differentiate this with respect to each variable. And you can see that we're going to have 4 different singular points at 1, 0, 0, 0, 0, 1, 0, 0, and etc. And that's this point here, there's one hiding back there, and there's one here as well. Okay, so this is what the geometry of these singular points looks like. Okay, in terms of the vanishing. So this picture here, this is the vanishing locus of F. Okay. Now, we're going to define the discriminantal locus in this case, okay, and as we're going to look at VP and we're going to collect all of those Fs which are singular, okay, all of those Fs which are singular. And as we said before, and this is called the discriminantal locus, okay, exactly, and we want to try and understand this discriminantal locus, okay, so described by Poly. So, right, so as we said before, this V of P is a finite dimensional vector space, okay? So we can imagine VP, so I just want to draw your attention to this part of the diagram here. So VP is a vector space, finite dimensional, so it's isomorphic to Cn for some n, okay? We put some coordinates on Cn, y1 to yn, okay? So this is we put some coordinates on C to the n, and it's, as it turns out, so in the case for the standard simplex, this is very well known, and it's very old mathematics. For non-standards, the simplex, it's not very well known. But this locus here can be described by a polynomial in the y1 to the y ends, okay? And this is precisely, so the fact that, so for the standard simplexes, it's actually, this is the discriminant, and it was found out 150 years ago or so. As for these more general simplices, the fact that this is described by a polynomial is actually, yeah, I mean, it's buried somehow in this work of Gelfand, Kapranov, and Zevlinsky, where you can actually show that this actually still is described by one single polynomial. Okay.
Is this a result just for simplices or for arbitrary polytopes here?
So you have to be a bit careful. So you for arbitrary polytopes, you have to insist a non-defect.
Okay.
So non-defect is this, because, yeah, so essentially you're looking at this linear system and there can be codimension too. So yeah, in fact this doesn't really appear very well, but there's these definitions in this work of Sandra De Rocco, who classifies the polytopes where this discriminantal locus has codimension greater than 1. But the problem is that for polytope, and this is still an open question. I mean, I've been thinking about it quite a bit, but haven't got anything complete yet. But these kind of, you're looking for defections, right? So you can always, which is a codimension 2 component, or so a component which is non-codimension 1, because they will still be non-defect, so they'll still be good from the kind of standard A discriminant Sandra De Rocco, Gelfand, Kapranov, Zevlinsky viewpoint. But it is possible theoretically to have other components which are of higher codimension. So this is, it's about the purity of this locus here, and that's not clear. And there should be counterexamples. I mean, you can cook up counterexamples, but it's not necessarily, they're not easy to write down necessarily. Exactly. So the first kind of example of a discriminant, which so people should think of as somehow reminiscent of kind of this high school math equation which one learns, x0 plus c here. So this is somehow homogenization of this kind of basic equation, and you can tell whether this is singular by looking at the vanishing of this polytope here. So v of p is equal to c3. Okay, so and coordinates are given exactly by these. The coordinates are given exactly by these coefficients here. So this is our 3 dimensions, and the polynomial in these coefficients telling us when this is singular or not is exactly the classical discriminant. Right. So yeah, and there does for weighted projective spaces, and there again. So it's not completely true. There are some really degenerate simplices which you have to avoid still. The other, for example, there are some really horrible simplices. Kind of, it's always very low dimensional, low degree, so not very many lattice points where this actually doesn't work and they are defect. But with mild assumptions, the simplices always, this discriminantal locus always splits up into this kind of decomposition. Okay, which is a product of A discriminants in the sense of GKZ. Okay, this Gelfand, Kapranov, Zevlinsky. So you really can describe this non-smooth locus as all of these of different kinds of these other well defined and well studied A discriminants. Okay, and thus we have a so I'll start to speed up now. So thus we have a decomposition of this non-smooth locus into these irreducible hypersurfaces, each of which are very, so I don't have time to go into it today, but they each come from other smaller polytopes. So they each come from faces of your original polytope. And actually the result is that you can only look at the faces of the polytope which correspond to singular torus orbits. And then you look at the A discriminants associated to those faces, and they give a contribution in the form of another hypersurface. And you can get this description of this discriminantal locus inside this vector space VP. Okay, and so the way I came across these is I was studying these some Del Pezzo surfaces, degree 1 and degree 2. So here's the degree 2 case because it's a little bit easier. So this corresponds to the weight vector 1, 1, 1, 2, as we said before, and degree 4. So it's the convex hull of 4 0, 0, 0, 0, 4, 0, 0, 4, and then 0, 0, 2, okay? And the discriminant decomposes in this case into so a more complicated standard discriminant. So this is actually the same discriminant as you get when looking at the plane cortex, corresponding to this part of the vector, and a hyperplane section, okay? So topologically, it's really, and I'm interested in studying topology of these spaces and of these complements here. There's a very, very nice book by Vashlev looking at complements of discriminants, and then this was originally applied to topology of moduli spaces by, maybe not originally, but at least most prominently, I think, by Tomasi. And exactly, so because the aim at the end, I want to study these smooth hypersurfaces, okay? Singular ones are kind of bad. So for now, in this perspective, I want to study these smooth ones. And I can, if I understand this decomposition here, then I'm on my way to understanding the topology of this guy over here, okay? And we have some computational results in this direction, which I won't have time to go into. So just some concluding remarks then, and that is that, so I haven't mentioned anything about any group actions or symmetries here, but there are within this vector space VP, there is a huge amount of symmetry, okay? And there's a huge amount of symmetry, and once we've taken into account this symmetry, it's equivalent to something known as taking a group quotient, but the topology is then accessible from this viewpoint. And then P being very ample, so the very ampleness of this polytope here that we started with is a crucial property in terms of the moduli interpretation, okay? And then finally, if you really want to study these discriminants here, they get very complicated very, very quickly. And yeah, exactly. So even for the cubic, you can't write down I think it's yeah, I mean, it's sat inside a, what is it, 19-dimensional project, a 20-dimensional vector space. So it's really, really very big, and it's a polynomial of degree 32. And these things are very, very complicated. Anyway, I'll stop there, and thank you for your time, your attention.